All right, let's get started. Thanks for joining for the NPA today, good attendance today. I'm happy to introduce Professor David Hertzog, who is the Arnold McDonald Distinguished Professor of Physics at University of Washington and Director of the Center for Experimental Nuclear Physics and Astrophysics. He's also a fellow of the APS, National Academies, recipient of the APS Bonner Prize in Nuclear Physics and a Guggenheim Fellow. We heard about yesterday his work in the precision muon physics in the muon G-2 experiment at Fermilab, where he continues to test the standard model at unprecedented precision. And today we'll hear about his work on the Pioneer experiment. So please welcome David.
So down, hopefully it'll run up. Anyway, thank you for allowing me to talk about this, as well as the experiment G-2 from yesterday, which is kind of a big deal thing that's over. But a few years ago, the origin of this thing was before we actually got any results on G-2. I was starting to think about what would happen, what should people work on, what should the postdocs and students think about in the event that G-2 confirmed the standard model or went the other way and looked like new physics. I had a whole diagram with a triangle like this, and I had the ball. It was at this point falling a little bit more toward beyond the standard model physics, but the new measurements would either knock the ball one way or knock the ball the other way. So I did a survey of everything I could think of in the world that would be valuable if it did this, or valuable if it did this, and also valuable if it, no matter what it did. Some things were no matter what it did, like neutrinoless double beta decay doesn't care one way or the other. G-2 turned out it was always in the, that would be a good thing to do in the future kind of thing. It is, not just because you guys do it. And it was kind of, I was going through this survey, and then I always do this when I have to go through what do I want to do next in life, because it doesn't happen very often that you get to change what you're doing. And you make a matrix, then you make a matrix also what you could, there's a lot of great things to do that I have no idea how to do. And I wasn't going to sign up myself for something I've never experienced. And so I have to have hold a little bit of reality. And one of the things I tumbled into was what led to this thing a little bit, which is the question of lepton universality. I noticed these experiments that had tried to do this experiment, and I'll mention them along the way, but had never been able to publish their data. And so a few of us went to a workshop at Triumph that was set up by the Triumph people on what should they do with the Triumph lab? Nothing, just this, and we were just one strand of it. We ran into a few other like-minded people, and at this point it's a blur for me to remember who said what and why we said what, but ended up with a group of people that started what's called Pioneer now. And so with that little introduction, I'll try to tell you a story. And unlike yesterday was kind of a not complete story, this is a story in which I'm going to ask you to think along with me, especially halfway through or more, because I don't really know how to do this experiment exactly either. I'm going to show you what we think might be the right idea, and I want you to pretend like you're in our group right now, where the whiteboard is still kind of sketchy, and you're coming in and going, I don't know, we should do this, we might want to do that, because that's basically the nature of where we are in lots of things, which has made it for all the young people and the old people a tremendous amount of fun. Okay, so let's see. So let me just start with some physicsy background, not too deep on it, but so lepton flavor universality is essentially, simple statement is, the weak interaction Baire gauge couplings among the leptons is the same, the electron, the muon, and the tau. We just take that as true in a way, and therefore the weak interactions, the strength is what we call the Fermi constant. We give it capital G F if it's like that, or if in high energy physics people, they probably have a little lowercase g, and some stuff you guys use a slightly different g. But anyway, this is the Fermi version of it with the contact interaction. And the way you get the Fermi thing is the muon decay. And I did this experiment where we measured the lifetime of the muon to a part in a million, and then you get the Fermi constant to a half a part per million. So this was an experiment I did before the last G-2 experiment. It's a small group of people. We decided we wanted to measure this thing because it was known, and the little corrections and so on and so forth that make it like that. But the thing about the Fermi constant done this way with the muon is that's actually technically it's the it's the muon Fermi constant. It's not necessarily the universal Fermi constant. And one of the things Phil Marciano wrote at the time, and I always kept this little paper around, was Fermi constants in new physics. Was the question is that really a universality? Is that really the universal weak interaction coupling, or is it just the muons version of it, which we then assume is good enough for everybody else? So the first measurement for Pioneer, the first motivation is a test of lepton flavor universality, essentially a test of this gauge coupling universality. So Pioneer will test this basic principle here at this kind of this vertex, if you want, by doing an experiment, which is the following. It's called RE mu. Sometimes you'll see this ratio RE mu, and it's essentially the branching ratio of a pion decay to an electron in a neutrino, and this little thing is a possible radiated photon, so it's just inclusive in that, versus its branching ratio to a muon, a neutrino. So you know that it goes to a muon, 99.99 something percent of the time. That's all you ever would think about, but about a very rare amount of time, it goes to the electron, so that the ratio of this is really something like 1.2 times 10 to the minus 4. So just for ballpark reasons, let's say part in 10,000. Part in 10,000, it goes to the electron. The rest of the time, it does what everybody always thought it does. It goes to a muon. Now, you notice here that the experiment is known to this precision and the standard model is known to this precision. This is 15 times better. So the standard model calculation of this, and this has the last, this is Sirigliano, it's right there at Washington and so on. It's a calculation which mostly, you get most of this for free if you want to get that business. These are the two diagrams you'd see where there was a GE here and G mu in this diagram. This is a ratio, you can look at that. I'll show you a diagram, a plot of that in a minute. But to very high precision, you can get this number yourselves mostly by just taking some of the phase space pieces like that. There's a phase space piece and there's a helicity suppression piece. It's really the helicity suppression piece which gives you this enormous setback of 10 to the minus 5, and then some phase space augmentations, and then it's really just these electroweak corrections and some tiny things that divide out because you're dividing a ratio. So any hadronic things just kind of divide out in that ratio, which allows the theorist to get this number to a part in 10,000. So, in the history of this, it's kind of interesting. This branching ratio is so small that a long time ago, it was just excluded as never being seen in a way, meaning, this small amount. So way back here in 1955 in Columbia cyclotron nearby, the ratio was, published as somehow less than this. And then just 2 years later, Anderson and Lutz had this measurement in Chicago, and they said it was less than 10 to the minus 5, which is very much disturbed a lot of people, including Feynman and Gelman, who had this wonderful thing in their abstract. This is the kind of paper people never would write these days. So they talk about these people measured this thing that 10 to the minus 5, and it says experimentally, nothing was found indicating that the ratio is less than 10 to the minus 5. This is a very serious discrepancy. The authors have no idea how it can be resolved. Imagine publishing a paper, you just wrote that, but if you're Feynman and Gilman, I guess you can get away with that. Well, it wasn't long before CERN opened up. One of the first experiments at CERN actually measured this thing. And so this is a great experiment which will take you back. If you're old enough, this will take you back to the way experiments were kind of done. But you would bring a pion beam in here, you slow it down through some kind of a degrader, you stop it here. Then you look at basically with a sodium iodide detector, somebody that punches all the way through that, and they got some events. So the pion decays to an electron very rarely. It's going to make a 70 MeV electron positron really at that point, and they found that ratio, and that ratio is okay. Now these days, just like yesterday's experiment, these days this can be a student exercise. So just a month ago or so, when we finished our test beam of our detectors at the Paul Scher Institute, the next people who moved into the beamline was the students from Heidelberg, Mainz, and Zurich in a practicum. They had a 2-week practicum, and they took our detectors as well as some of the other detectors, and they basically repeated this experiment. And not too difficult. They were able to get the spectrum here this is just online for them with enough cuts. This is basically the pi e channel. So it becomes a student exercise at that point. Now you got to take it to another level. So the aim for us is is a 10⁻⁴ level of precision on a number which is 10⁻⁴. So right away you should be scared, leave the room, and I don't mind if you do. It's that kind of, I thought we could do it until I learned more and more about it. So I'm adiabatically going down into a complete and utter doubt that this is doable from my naive beginning of this, which thought it would be equal to do, easy to do. And I'll tell you why it looks easy to do, and then I'll tell you why it's not. And that's where I want you to engage your own selves. But why would you do it? So many beyond the standard model scenarios these days can be evaluated with this thing called standard model effective field theory. Standard model effective theory, where you look at these kind of couplings like that, and you can figure out what mass scales are you testing. And one way to think about this ratio is it should be 1, but there could be a little epsilon from mu, mu, or EE. And these two things being different than 0 actually can, in another complete use of this, explain the unitarity problem with the CKM mixing matrix. It couples it exactly. So if those numbers aren't that, you can actually you could get a 2 for here. You can find out the lepton thing, and you can adjust the unitarity. So a nice paper on that, the top director and others. But if you look at the scale of the violations of this, this is where precision physics does a good job. That's well beyond the collider. You can see by the numbers. So for certain beyond the standard model axial currents, you're testing 30 TeV, and for pseudoscalars, you're really at 1,000 TeV scale and mass scale. So that pushes it way, way, way out there. And that's why we design these little experiments in lots of areas of physics that have this probe to tell us the direction to go in. I think the easiest thing we did is made this plot for ourselves. This is the theory right here for this ratio, and this is the one. This is the compilation of the best measurements right here. You can see this line just kisses this line, and this is what we want to do. I don't know where this will be, this green thing, but if it's over here, we'll be very happy. But of course, if it's over here, like yesterday, the theorists will change their mind. That's my prediction. Second idea that we could do with an apparatus for rare pion decay is do an ultra rare pion decay experiment, which is the measurement actually of pion beta decay. It's a 10⁻⁸ branch. It's a tough one. This is really the nuclear physics one. So the particle physics was the first thing I did, and the nukes like the second one. So the particle people like the first phase, and nukes like the second. Go figure. So if you look at that thing I mentioned before, this is VUD, this is VUS, this is the CKM plane of the first two elements, and you can forget the other one. This is all you need to see to get unitarity. And this line here would be the line of unitarity, which would kind of go all the way around some of the squares of those elements. It has to be 1. But if you look at various kaon, which is VUS measurements, or the ones in the nuclear physics community, which do VUD, which is either the 0 plus the 0 plus super loud transitions number, which is now blurry because of the radiative corrections, or the neutron numbers, which are kind of uncertain because of things like the lifetime and the asymmetry for that. And then the best fit, it just doesn't work. These runways don't cross where they're supposed to cross, which is on the black line. Typically, they're always 3 standard deviations away from unitarity. It's frustrating. For my whole career, it's been 3 standard deviations, but it's different 3 standard deviations because the precisions are getting better and better and better, but the 3 keep staying. So it's kind of a weird thing. I don't know if it's VUD the problem, or these VUSs, which look kind of funny, but there's something. So this is the way the precision looks by super louds, and all of these things are corrections that are large. So the corrections are very large for this field, but in the pion beta decay, this isn't right. This isn't up to date. I'm sorry about that. But basically, it's an extremely clean way theoretically to do it. It's just way, way far behind statistically. It's super hard to do. But we thought, well, the one was hard. Why don't we do the other two? And so pion beta decay, this is kind of interesting. I showed you that little historical thing with the Feynman and all that, that first publication of that. It turns out in the old days of PhysRev letter, the one article was very short, and they just ran around to the next one. So you would print one out, and you'd see the little taste of the next one. You'd see a little paragraph or two of the article. Everybody's nodding. This was the one that, amazingly, this was the one that was right afterwards on the beta decay of the pion, where they looked for this with a completely different team. And I think it was bubble chamber and everything. And they looked for this thing, but they only had 6,000 or so events or so, and there's no chance you could find that. So they put a limit on it, but it was kind of cute that it was right there. The way you look for pion beta decay, though, is not so bad compared to the other thing. The other one's going to be tricky. The one we're going to do at first is tricky, but this one looks, except for the 10 to the minus 8 problem, it's easy. It's an easy signature. You're just basically looking for a back-to-back gamma ray from pi zero decay. So in this reaction, this positron doesn't go anywhere. It just barely goes anything. It's so light. So all you really do see is boop boop like that afterwards with a lifetime of the muon. So you can collect those reasonably. You do have to normalize it. That's the tricky part, but okay, apart from that. And so the pion beta decay concept in our experiment using a kind of, there's two calorimeter ideas. This is the one I'll mention a number of times because it's the one I've been pushing. It's a segmented detector that has 311 crystals that are all like that. And so of course you can naturally do this, and we basically work this problem out all the way through the system. And we think we could do reasonably well, but not as good as the experiments like that. So we think we could get a factor of 3 and then a factor of 3 again or so, and be compared to these two different discrepant versions of VUD. We would at least get a little bit in the game with a different point of view. It'll be down the line, but it's to be determined how fast we could do it. But the aim is 3 and then 6-fold improvement, just going through the numbers that we think are available, the beam that's available, and how fast we can take data. Now, this isn't necessarily my particular cup of tea, but it's really important to lots of people in the collaboration. And in the previous collaborations, they've actually published a lot of papers on that. When you see the huge data sets that I'm going to be talking about in the huge spectrum, you can sort of search for those for sort of deviations and bumps and things that might be axion-like particles or be heavy neutrinos and so on. This is a limit. This was in the SNOMAS, followed from the SNOMAS study, the people that were putting all those things together. And the pioneer limit is this, I think this new dotted blue line would be the pioneer limit that would come along and pushing these numbers down from where they are. So it's, there's literally actually a lot of activity on this, interestingly enough. A lot of models and a lot of different things to look for various reactions of pi to E and these different kinds of exotic things. They could either be a bump or can be a distortion in the spectrum overall. And you'll see that spectrum in a minute. So that's the end of the little physicsy motivation things, those three kind of things. And I would tell you that this is an approved experiment. It's a priority experiment they call a flagship experiment at PSI, a next flagship experiment. So you do get a lot of resources that when you work in a lab like PSI, if you've never done that, it is an absolutely treasurable place to go. They support, the beam is there, the people that take care of the detectors and help you with anything are there. You don't pay anything for it. It's just really fun. And I've done a bunch of experiments there, and I think from a student experience, it's the best teaching place we've ever had. So here's a cartoonish way to think about this experiment. So this is now the time when you have to engage yourselves and think and helping along with me. But I have to remind you of some stuff because unless you're doing this stuff, you won't remember these numbers necessarily. So first of all, pion has a lifetime of 26 nanoseconds. And a muon has a life of, 2100 or 2200 nanoseconds. So these are very discrepant. So if you look at the one, if you stop a pion, it's going to disappear with a curve that looks like that at 26 nanoseconds. And if it instead goes to the muon, it's going to go to the muon, and then this is the spectrum of a positron coming out. So the positron comes from the muon decay. So you're going to have it build up from that one and then decay with that very long time. And this long time constant is so long that typically another pion might have come in while this is still living, which is a problem. So they're usually living a long time, well past the time that we begin to look at the experiment. And this is the relative masses. So what that means is if you look at a pion, let's do the red one here. If you look at a pion going to the electron, this is the rare channel here. Then of course you just take the mass of the pion, divide by 2, and you get about 70 MeV. So that spectrum is just like this. It's a stick. It almost looks like your nice little double beta decay, your little treasured, like that, if it could only be, right? If it could only be, except it gets much worse. And then the muon, the pion going to the muon, produces the muon spectrum, which we call the Michel spectrum. Michel's a 3-body spectrum. So it's muon goes to a positron and then 2 neutrinos. So it mixes the energies, and there the endpoint is 53 MeV. So this looks easy, right? You measure this and just divide those two things, no problem at all. That would be at walk home. Now, the reality of that is, how do you measure a 70 MeV electron like that with this little precision I've made of like fractions of a percent? And the answer is, and that's all you would have to do, put a threshold there. And the answer is you can't really get that with a realistic detector. A realistic detector is going to be like this. And you're going to have a tail. And this tail is the phrase that matters, because this tail is typically at a really, really good detector. This is going to be at the level of a percent maybe of the thing. And this can happen because things like a neutron gets knocked out, or somehow you lose a little bit of that 70 MeV. Very easy to do in low energy processes involving a positron trying to interact with matter. You are not absorbing it all. Now, this in the noise, this would be nothing, in a collider. You're up here and you'd never see this, but this stuff is the leakage that happens even with a detector, which is rather comprehensive. So leakage at the level of, you probably, if you know the word albedo in calorimetry, if anyone's on that, that's just what bounces off the front of the darn thing. Is you go in there and some energy comes back out. You can lose one positron, you can lose a few, you can lose a lot of things like that. So inevitably, this calorimeter design is super important, but there's no design, no matter what on Earth, in which this is 0. So now if this is, let's just use the numbers. Suppose this is 1% hiding under here. If this is 1%, I have to know this 1% to 1% to be 10 to the minus 4. Okay, so that's a challenge. So how do you see the tail when it's blinded by the background of these guys? And that becomes an issue called the tail correction. This is a real Monte Carlo. We, for a long time now, from the very beginning, unlike the other experiments which tried to do the Monte Carlo after they built the experiment and couldn't analyze it, we have a very comprehensive Monte Carlo that we've invested in for years at UW, and which every piece of material that we're inventing is in there. Every reaction, every bubble scattering, every low energy thing, every cross section, every physics process in Géant that we test between different physics things has been in there. So our real picture looks like this. So these same little cartoon, here's the red one again, and you can see it like that. In fact, for the calorimeter that I hope we do, mine is about 0.5% in this tail. This is the Michel spectrum, and then you see these other lines. And these other lines that are important, for example, are the green line is pilot. It's just from typically old muons and things that are around. And you can't make them go, you can't make them die if they just sit there somewhere in the apparatus and then boom, they shoot out a positron into your experiment. And this one is pion in flight. There's a few things I'll show you that are really, really nasty coming up. And you get the idea right now that you have a difficult challenge, at least of dividing these two things at the level of 10 to the minus 4. And okay, I have written the tail, muon decays in flight. Oh yeah, okay, muon decay in flight. So a muon gets born, and suppose it's just moving, and it only goes about 800 microns, and it only has 4 MeV. And it has a lifetime of 2200 nanoseconds. But still in the first few hundred picoseconds, it has a chance of decaying, like anything does, and it's moving. Now, if it's moving, it's going to boost the thing, it'll boost the electron that it shoots. And that boost will go, instead of this line here, it'll walk itself into this line. So just a kinematic boost from the rare possibility that in the first nanosecond, a half a nanosecond, that a muon decays, it can push a positron into the spectrum at a level of, at the level you can see compared to the peak. You have to account for all of that kind of stuff. Okay. So like I said, why is this so challenging? Well, I also had this little expression here where you saw this R here, R epsilon. This represents the efficiency of the detector system, triggers, and so on and so forth to realize either one of these event types. So I just call that the efficiency of either type of event. Now, why would they be different? Well, this is a spectrum. This is straight out of the particle data group book. Somebody said they're going to an instrumentation conference. I was thinking about you in this plot, okay? This is for you, this plot. So this is 1 MeV, 10 MeV, 100 MeV, and a GeV. Okay, and these are the cross sections processes of a positron going through material. And this is the 70 MeV went out here, and it's just the usual, bremsstrahlung. It's just what a normal electromagnetic shower would do. Anybody who's built a shower detector just only lives way out here in their brain about how they interact. They and they shower. But the ones in the Michel spectrum, which I painted in the color, are being dominated by other processes: molar scattering, Baba scattering, annihilation. All these things, all these processes are coming down rapidly. So this is the way the Michel ones look, and this is the way and that means that any matter that the positron goes through, any detector, any trigger, tracker, or so on, is now different. And now you have to know that difference at the level of better than percent. Okay, so there's that issue. Then you need high statistics. That's just means you can't just run at a comfortable rate where you could get rid of the pileup and wait for things. You actually have to run pushing the envelope on that. I'm not so worried about the DAC. I'm not worried about stuff like that, although it's very, very high. I'm just worried about how do you collect the number of data that you need to do. And the strategy is essentially that we come up with is a very, very innovative imaging target. The idea of this imaging target will be that we can tell you what those two processes were right at the stopping location. And then from there, let's see. I do at the end have a little bit of the analyses. We're actually already developing all the analysis programs. Yeah, by the way, shout out. This is like a lot of kilograms.
Yeah, so starting to wrap my head around this, the high statistics, there's a trade-off between intensity and playing around with timing structure.
Yeah.
Right? So you don't have wiggle room there in terms of turning up the intensity and stretching out between arriving particles.
Okay. That's a great question that calls, what is the beam?
Yeah.
So at a place like the Paul Scherrer Institute, the beam is quasi-DC. By quasi, I mean it's DC, but it has a microstructure of about 20 nanoseconds. So like that. Otherwise, it's 2.4 milliamps of protons. It's amazingly intense, and it's like a battery. And it's all like that. So you're getting so they're coming at you. Because the time of flight of these non-relativistic pions is coming in, they're kind of coming in a little bit smeared, but they are clocked to that 20 nanosecond thing, which is then different than an electron coming in or a muon coming in because they have different time of flight.
And you don't have empty buckets as an option.
No, there's no empty bucket
I see.
thing.
Okay.
It's full, rich. I know exactly why you asked that. That would be great. So the previous generations of experiments that still haven't published their final work look very, very differently. This is the one that is been successful. This is a big sodium iodide crystal like that, surrounded by some cesium iodide. And they had a little bunch of scintillators and tracking thing like that. And they had excellent resolution. Sodium iodide is very good. It's very slow. And they ran this very slow, but it's okay. But they had very good resolution for that. So the shower leakage, on the other hand, was dependent on the angle. And then the other one was an experiment. This was called the pi beta experiment. There was an experiment designed, the one measurement of the pion beta decay is this measurement. And it was very beautiful for that, symmetric like that. But these crystals are pretty small. And they tried to turn this experiment into an experiment to measure pi e nu. And they've 13, 14 years ago, they've still never published this. They're trying. There's too much leakage. The resolution was terrible. The crystals were bad. It's a sad story in a way, but they're still trying to do it. But these are experiments that are left with, one person after 12 years is all by themselves trying to unblind it. So that was and they're in Pioneer, both of these groups of people. I mean, we have you don't start inventing this without going to the experts in the world, even if they've struggled. They're going to tell you what they've learned. They're very, very much a part of it in that way, especially the Pioneer people. There's a lot of them. So in any analysis, just to tell you, you have to get this ratio of these two. You have to get the tail, and I mentioned the cross-section dependent physics processes there. You have to count the events in this high bin essentially, and counts in the low bin with from the shell thing, the tail from this thing, and this thing here, and just a little example of the tail thing at the lowest energies. This is the Michel spectrum. This is just the muon to electron Michel. And this is, like maybe the Monte Carlo, and then all of a sudden it goes wacky. like that. And it's just the stuff like that that's enough to throw you off. So the generic, this is a generic design cartoon. The beam is converging. These beams, for those of you who use colliders, you think of a laser beam. If you have a beam that's coming from a proton, which then makes pions, which then go, are flying off like in all directions from a target, you're collecting them with a series of magnetic lenses. It's an optics problem, which I'll show you in the next slide. It's just an optics problem, but the beam will be converging literally like my arms. And you're going to try to make it come to a small thing. So this isn't so disrespectful of what happens here in the shape that I've done. And you're bringing it into some kind of a target, and then you want to see the thing come out. So the idea is something like that. With 100 times the statistics of the previous experiment, which is why we have to run hard. And you want to measure these energies here, but you want to know what's going on in here. So how do we do
One more
that?
quick question,
Yeah.
how spatially constrained are you in your setup? I mean,
This thing here is to scale right now, practically on the screen.
I guess
Okay.
the question
So this
is,
is really tiny.
if your beam window is coming in,
Yeah.
are you hitting the outside on those corners of your
No,
detector?
we're gonna miss that
You-
completely.
okay.
Yeah. And we'll have that all, that's too cartoonish. I'll get a little bit more specific here. So first the beam, and I realized that I talked to somebody yesterday or today and said, we actually have to tune our own beam. So one of the fun things about an experiment like this is you're given the keys to the magnet closet, and you have to tune the beam. I'm gonna stand over here so you can understand what that means. So a place like PSI, the 2.4 milliamps of protons are blasting through a little target station here. This is target station E. There's a couple of them, and there's beam lines that sort of view it from different sides. So that means that there's magnetic lens right here, which is going to bend these particles, and then all of these quadrupoles and sextupoles here, and so on, all the way out. This is all behind a very hot rock wall area, which we have no access to, and has been built decades ago, and most people who did it are long retired and so on. They haven't run this beam line for pions in a very, very long time. It had the name Pi E5, probably because it was used for pion experiments 30 or 40 years ago, but it's only used for muon experiments now. In fact, that what sits here right now is the mu E gamma experiment. We're in the mu E gamma beam line. Okay. And then the mu to 3e beam line also. They're also using it. So you know this, Sarah. So anyway, we get these beam, and then it's interesting, you're coming through here, you make a right turn bend and a left turn bend. So there's a bend and a bend, then there's a triplet. That's nothing more than a lens, magnetic lens. And there's a velocity selector. A velocity selector is you probably did this problem once in your lives, it's the ENM problem. You basically go through an uniform electric field, typically a few hundred kilovolts on some plates. And that basically bends the particles differently, basically on how long they spend the time in there. So if you're a relativistic particle, you zip through. And if you're a slow pion, you start drifting down. And so at the end of that, you then typically have a system where you focus it on a slit, then refocus it. They didn't have that, so we didn't have that yet. So we measured the beam here a couple of years ago just to find out what kind of a beam we got, and it was compared to the size of our target, which is this box right here. The beam was much bigger, but we did have the flux that we needed. We could see that the beam was there, but not enough tuning elements. So that was a first effort. We could get the 300,000. We could get the momentum. The spot size was too big. The uncertainty in the beam momentum, what they call delta P over P of the beam, this is the momentum distribution, was sort of okay, but we needed a second focus. So we know we needed, from the beginning, anybody who's done this, we've done this a lot in my life, you immediately know you have to actually do something like this. You go through the separator, then you put a single element there, you slam it into a slit system, and then you refocus it. So we've designed that kind of a beam. And that's kind of one of the grad students, this is from one of the grad students at ETH Zurich who's been doing this work. And just to give you a crazy idea, if you were a pion and you made it to here, which like to here, the chance that you got to here is only 18%, because that's how fast the decay is and how slow the particle is. So anything that extends that beam line a little bit longer to make a better focus is costing you flux all the way, and they don't just disappear. It's not like that pion just goes, I decayed to nothing. I decayed to a muon, and suddenly there's muons flying down the street. So now you got 80% of the original flux is turned into background muons that are flying in random directions at the experiment. And it's not nice. So this is more realistic of what we're doing now. So what we're doing now, and again, this is a shield, Sarah, this is not the beam envelope this time, because we are thinking about a big veto shield which collects. So we haven't designed that yet, but we think we have to have that in the trigger. We have to know where it is. And we're going to try to bring the beam into here. And the idea is to build this little box right here, which has 48 planes, which are 2 centimeters by, well, 20 millimeters by 200 micron wide strips, 120 microns thick, and there's 4,800 channels in this box, which is just as big as my fingers are right now. So it's 5,000 channels in a thing this big. And those channels, I'll show you what that technology is. It's kind of cool. It's totally state-of-the-art technology, still being developed, still coming out of foundries right now as we speak. And you get XYZ position. We get 5D tracking is the idea. You get 100 picosecond timing. You get the positions. And basically the idea is to get the energy deposited in the silicon with a dynamic range of almost 200. So you know the difference between a minimum ionizing particle and a heavy particle that decays. Looks kind of like that. So the idea of this, the whole motivation is that if you can actually identify this channel in a subset of the data, you don't need to know this on everything, but you need to know that this is called the response function of the calorimeter. You just need to somehow measure it. So you can cut like mad. Don't worry about the ratio. You can do whatever you want to do to get rid of this blue line. And if you do that, then the way we think we can do that, we can wipe out by about factor of 10 to the 7th or so, and then finally see for the first time ever the line shape. Once you see the line shape, it's the same line shape. And so then all you have to do from then on is see this thing and then make the correction on the real data, on the full data set. So that's the basic idea. Typically, people use silicon detectors like this with minimum ionizing particles. They basically just have typically a simple layer like that, a p-n junction separated by that layer, and there's no gain particularly in that. It's a nice efficient thing. But the new idea that's emerging in lots of places in the last bunch of years, the electron ion colliders using a lot of places, is something called LGADs. We'll hear that word probably in the future more often. And these are so that same thing with a little gain layer in here. So there's a little bit of doping in here. And when I see they're still coming out of the foundries with different things, the idea of how deep is the gain layer, what the percentage is, these are all different versions that are coming out of different companies, FPK and Hamamatsu and stuff like that are trying these things. And how they separate from one channel to another, whether they're AC coupled, whether there's a trench in between them called TI, trench isolated LGADs. These are all different variations on a theme, which we've been exploring with lots and lots of test sensors at our lab. So there are silicon diodes with the gain layer. They have signal amplification, which doesn't exist really, and enough that you can really see it. And then they have a gain mechanism that we have to worry about the saturation for. And then what we're doing is, if each one of these planes built like that, then has to be built. What we're trying to do this very year, in the next 12 months, is build what we call a demonstrator. This is the ATAR demonstrator. ATAR stands for active target. Active target, we're trying to get 16 planes, but we have to get these trench isolated LGADs from somebody who's ordered them a year ago, and they're giving us sensors that we can put together. So at our lab, we're trying desperately to put all this stuff together. And the way we characterize this, and this is a brilliant idea of Peter Campbell's, I think, if you want, you could go over to PSI and fly over there and spend a lot of money and try to get some pions once in a while, but really could just to look at a tiny piece of silicon and see what it does. The best thing is that we have the Bandigraph at our lab at SEMPA. And this Bandigraph at our lab has a program that we do often for the students, but now for ourselves, which is Rutherford backscattering. So we can bring a proton beam in here at whatever energies, do Rutherford backscattering, and then with the Rutherford backscattering into the thing, a proton of 12 MeV looks like a pion of a few MeV in terms of its DDX. So we can actually mimic the exact pion or muon right in the lab. We spent 3 weeks doing this summer. And that was the third test beam campaign already that we've done at the lab. Characterizing the sensors gives us, now there's hundreds and hundreds of these plots with every incident angle, every voltage, every energy. So in every dimension, of all sensors samples that we had many different samples from different companies. So that's a comprehensive paper that's being developed, worked on right now by one of our graduate students. A lot of people got to do a lot of real hands-on work right at the lab. It was very effective. So the big worry actually is, and this is just driving them crazy. I mean, I'm not in the ATAR group, but I'm like the consultant who's not in the ATAR group, but in the room with all the ATAR people all the time. And I can say this drives them nuts because they're really worried about saturation effects. If you go straight through the chart, the ionization can come up, build up and hit the thing and not give you representative of the pulse that you think. But if it goes at an angle, then it sort of isn't diluting itself. And so they're getting a different, they're worried about this saturation. So they've got a curve that kind of characterizes it. This S is this distance here, this is DE, DS. It sort of looks universal. And just last Friday, we came up with another interesting way to calibrate the whole thing that we hadn't thought of before. So we're sort of just all trying to figure out how this thing works. This is new technologies. And we really thought that the many different doping layers that were available from the companies would hugely affect this problem. For us, it's a problem of can we identify something or are we confused with the energy response? And I think we're getting our head around that finally, but it's definitely a work in progress. So here's what happens inside. Now imagine this is now this LGAD. These are some of the planes of the sideways looking thing. And there's 4 typical things that'll happen. So the pion can come in and come to rest here, and then out goes that 670 MeV. That's wonderful. That's nice. But it can and also can do the other thing I said, which is go in, stop here. Then it emits a muon, which doesn't go more than 800 microns. That's the limit of what it can do. And then out goes the Michel spectrum. But it can also come in here, and on its way in here, because its lifetime is so darn short, it can decay to the muon while it's in flight, which then makes this purple track probably not too deviant an angle. You now think that this purple star, this is the energy of a high, what they call the Bragg peak, I'll show you. That now looks like, you may think that's probably the pion now. Now this looks like the pion decaying to this thing because you thought that was that. That happens. It's rare, really rare, but too big for us. And then this one goes in, this one now stops a pion, and now this was what I think I mentioned before. Now the muon is it's on its way to stopping, and while it's stopping, it shoots this thing out, so you never actually see the muon. So now you connect this purple track to this blue track, and now you don't subtract, and now you don't see the tail again because of this problem. And I'll show you how we got around that with right now, how our artificial intelligence program nails that, where our brains, who our rule-based thing, which connected this to this, got it wrong. And our artificial intelligence goes, no, I see what's going on there. I'll just skip that. So here's how this appears for this channel, pi to E channel, comes to rest here. And first, we have another little detector out there I call DTAR. You can imagine that's called degrader target or something. It's the trigger. This is the T0. This goes in your stuff. You get this one, Sarah? We don't even know where to start the clock on this. We have to look forward and backwards in time. We look minus 300 nanoseconds to plus 500 nanoseconds around the time that this thing fires. And we try to look for record the history of what it was and see who seems to have gone with whom. So in this thing, as the particle goes through here, I made this plot where basically the energy deposited in these little strips is moving along like this. And then this is what's called the Bragg peak. At the last few steps, it just rises. So if you can see that with the dynamic range of the LGAD, bang, that does not look like a minimum ionizing particle, because this is what a minimum ionizing particle deposits in the same thing, nothing comparatively. So they're extremely distinct, but that does give you an enormous dynamic range that this detector now has to be able to be honest and report back to you. Now, on the other side, when the muon is emitted here, then the muon is very heavy ionizing, and it goes not too far, 800 microns, and it does the same sort of a thing. And you want to catch that same thing again with the MIP being way down here. So it's quite distinguished if you can get that stuff. So minimizing the tail, then you go to the calorimeter. So that was a little bit about the active target. Now the calorimeter in the example I gave of the pion experiment with the single crystal, if the event went this way, this was a beautiful experiment. If it went straight like that, nicely contained, this is their response function that they measured. You can measure the response function, by the way, by just turning on an electron beam. I mean, you can just forget the pions and just actually measure it. So it's not that impossible. But as soon as they got any events that went at a slight angle, this percent level thing went to many percent. They only published this like a year ago, and they were never telling us about it. It was a little frustrating. It was very amazingly bad and challenging. So they had the problem of angle, but they had resolution and they had depth. And the Penn experiment had the opposite, which is it had all the nice acceptance, so it didn't matter if you went this way, this way, or this way, the Penn experiment particularly, but they had no depth. So we needed to design something that had that shape in the cartoon, which is why the cartoon shape had the kind of symmetric-y looking thing, plus also the depth it has. And for those of you who do calorimeters, well, 19 radiation lengths is actually a lot, especially if all you think you're stopping is 70 MeV. It's almost comically larger than you need. In G-2 it was 15 radiation lengths for 3 GeV. But we didn't need it. So this was the original idea of the experiment, was to, following on what Meg does, this was an idea of a big ball of liquid xenon like that with sensors all the way around there and maybe sensors away in there. And then we started to look at what that did in event displays, which basically would light up all 2,000 sensors every single time and not be able to distinguish pileup and so on. So I started getting involved in the development of LISO crystals. So this is the size. These are now proportional to one another exactly. So I started looking at that with some people from Shanghai and Zurich and us, and we've been sort of two like mini groups working together. So they both have common features, though. They made a fairly fair comparison. They both give about 30,000 photons per MeV, which is a ridiculous amount. That's like sodium iodide is stupidly high. They both have the same kind of decay time constants. They both are aiming for resolution below about 2% at the critical numbers. And they both have pretty much the same kind of timing from waveform digitizers. We do everything with waveform digitization, so we get good timing on it. And the differences, though, are the LISO is segmented. And can be read out with PMTs at 420, just standard PMTs with good phases. The liquid xenon, you guys all know the wavelength of that is nasty. What is it?
175.
175, yeah, that's a little challenging. So you're in this VUV, so you have to have sort of special sensors, either phototubes or the SIPMs that can read that. And there's a lot of them. Now it's 1950, this has changed again. And the data load, xenon's actually a couple hundred times higher per event because everything fires on every event. So and the downside of LISO is it's radioactive, actually, it's slightly radioactive, which turned into a good side because it's self-calibrating, it turns out. So we bought some, we got them going. So what is LISO? This is the long word, lutetium, yttrium, oxythoric, something or other. And but it's the cerium doping in there that's the scintillation compound. So it's the delicate recipe that the growers of these crystals put in, which determines the light yield. And it's very dense. So radiation length is only 1.1 centimeters. So it's incredibly dense and very heavy, compact like that, almost like lead. And the Moliere radius is much smaller. We hadn't appreciated how good that is because when the Moliere radius is a measure of the width of a shower in these units. And like for xenon, it's much wider, which means that things could spread out significantly. So you want a dense shower at a smaller radiation like, then the other things are just numbers for you to know. So this is what we first started by just looking at rectilinear crystals. The people in mu-to-E, if you remember the old history of mu-to-E, they did this. They looked at these crystals, they had their crystals, and we studied their paper, and I decided in reading this paper a few times that they got resolution at about 4% or so at these energies. And we wanted 2%, let's say. And I just kept thinking, well, most of it was what they didn't do right very well there, which was basically the beam itself had a delta P over P, which is 2.5%. But 4% is all they needed in mu-to-E. So it's perfectly fine, they didn't care. So I thought, this got to be better than that with 30,000 photons. So we just went to a beamline with a delta P over P of 0.5% or something. And we built very careful, and we got custom crystals and worked very, very closely with the company on these crystals. And basically we ended up with, well, I'll show you some neat things about LISO first. First of all, it's unbelievable, but a calorimeter crystal can resolve things like the 511 lines, split lines in cobalt 60, and sodium 22 lines. We make our own sodium 24, I should say, sorry. We make that at our Van de Graaff. We can map out all along here the uniformity of the thing. And this is only up to 5 MeV. So the resolution was extremely good up to 5 MeV. And then when we went all the way up to 100 MeV, we basically at our goal got 1.5%. So it's 3 times better than what people had done in the field before. So they really did come through. And then we got this point here. Something went wrong here because we went back to SEMPA, our Van de Graaff, and measured this line that people use for calibrations. This line comes from using a 0.5 MeV proton on a lithium foil, which gives a 17.6 MeV monoenergetic gamma ray. And a little bit of history on this, it goes way, way back. Renwan from Caltech, I think, invented this in a single author paper. I see it. It was the basis in which the L3 experiment at LEP, the giant experiment, used this method to calibrate their 11,000 crystals, which they used at high energy physics. I'm like, what? They used a little Cockcroft-Walton to do that. So we actually did this at our lab. We brought that same array back and did this because what was happening here is our 2 bases were completely flawed that we got from Hamamatsu in terms of their noise energy. And we had to rebuild all the 2 bases and throw away a lot of them. So when we went back, did this later, then back to PSI a month ago, we got good resolution here again. So really it's like that. So then the next step was also timing. Timing wise, we got 100 picoseconds for anything that matters. So that's pretty reasonable. But then we had to do it actually with the geometry we wanted. So having solved that thing, we had to now invest in these things, which are about $40,000 a piece. So you don't just buy them for fun. And we had to develop all of the geometry, all of the techniques to mount things. And our engineering staff at SEMPA are so amazing and come up with these little things to mount in the back. And we built an array, which is unlike normal calorimeters, where you can take out any single detector at any time and replace it if you want to. It's not locked in like by the geodesic dome kind of locking. It's really very, very clever. And so we got an array to build. This is the sizes of everything. That's a cup, like you guys gave me a nice Yale cup yesterday, which I'm very happy to have. Thank you very much. Treasure it. I like it very much. And so we just did that. This array is all we could afford was 6 of these. So it's not big enough to contain the shower. So we know the leakage, but compared to our measurements, we again did the same thing and got very good 2% resolution. And the rest is leakage. We know that. And then we also got better resolution than we did before. And this just goes to show you, forget the log plot, go back to linear. This is what it is at 70 MeV. It's a pretty nice looking response function. It's just the stuff down here that I'm not showing you. I love this. I came up with this idea. This is the Cockcroft-Walton that sits there for Meg. And my animation, I don't think I have the animation going. Do I have the animation? That's so cute. Yeah, I do. Part of it's good. So this is what you can do with this kind of calorie. Probably couldn't do this with liquid xenon, roll it. But what this is, you do this 3 times a week. Get down here. You whip it around. And it's all on board electronics. All the digitizers are there. You go into this thing, and out comes the protons into the lithium target, and you calibrate everything at once. Cute. I like it. Okay, what else? The other thing you can do is you can bring a pi minus beam in. You bring a pi minus beam into a liquid hydrogen target about once a year. You substitute that, and then you get this pi zero decays. And the other thing is there's a laser system that sort of mimics what we did in G-2. I don't know if we need this. I drew this before my incredible graduate student, Omar, realized that you could actually pre-calibrate all of these things with their internal radioactive decays and get pretty good. And then you do this thing, and then we calculated that the pi E comes in so fast that we can calibrate every crystal by having it be the lead the lead crystal, and we do that in 24 hours. You have better than you could ever do it, and you have it at the energy you want. So yeah, to measure the line shape, you gotta go from here to here. And I maybe am repeating myself a little bit here, but you have to veto these. So you're really looking at vetoing events like that. And I think I have a better kind of animation of some of this things in a minute, but now I can leave that off. It's okay. I don't want to stretch this out too long. So the pion stops. You have to figure out, here's what you have to do in the analysis. You have to figure out where the pion stops. It's important to know it was a pion that came to rest. You have to figure out which way the positron came out. It's a bit feeble looking, but it has a lot of hits because there's a lot of planes. And then you have to reject these kind of events to get that tail revealed. And the basic steps are you get some hits and you time group them. So these are all grouped that, they're all 100 picoseconds. So let's say 1 nanosecond, you decide all the blue ones have fired within a nanosecond. And so you get a T0 to start that thing. And then later, actually, most of the time, this is a lot later in time on the scale of nanoseconds. This is a lot later. Now you time group the green ones, and they have a lot of different. And then later, quite a bit later, actually, that in general. So most of the events are really topologically very easily separated in time. I'm only usually showing you the nasty little things where stuff bounces into each other, and that could be tricky. So the ones, so this is the thing. So in a rules-based basically means that, you're given the task of doing what I just said. You make up a code, you grab things by time, you make a little track, we call it tracklets for these little things. Then you hand that off to somebody else who glues that tracklet to that one and that one to that one and comes up with it. It's all like logical, what you think as a human you would see. So we try to do that. And when we do that, we make mistakes because we haven't folded all the information in yet and so on. So we can do it pretty well, but our current version, it still has gaps in it that doesn't. So my student Omar has gone down a completely different street, knowing that this is the absolutely ideal problem for an advanced AI ML with a learning model, not a trivial model. So he wrote some of this for me, but because I told him I think it's a bit like being a detective. So he followed my theme. Each event is like you're a little detective and you're on the hunt and you're looking for clues, and you need to be able to ask those questions. So you kind of have to say, what are the fixed questions in a neural network? He said in a regular neural network, there is a fixed set of questions. They likely give the same weight and so on to each answer. Like going around the room and I could ask you each, where were you last Tuesday night? And not really start to do the correlations of what might have been more important with the crime of where you were versus where you were on Tuesday night. If you work it out like that, a neural network's a bit more agnostic like that. And the new thing called a transformer network, where this graph-based approach learns to ask the questions going around and realizing that you're sitting next to him and the two of you were where, and the difference between the two of you where you were last Tuesday night becomes more important than where you each were last Tuesday night in this crime that we're trying to solve. And so that thing is amazing as it starts to learn about hit relationships of neighbor hits in that little group. Not just that they're in the group, but who's next to you in the group. That becomes more important than the group. And so just a thing like this is just one example that popped out right away. This is the difference between the prediction of where the pion stopped. So 0 is the correct answer, or something like this is the correct answer. And in the rules-based approach, you would normally get, this pi nu, you would get okay, but when there's a Michel event, we would see that we get that, but then all of a sudden we get it over here. This is 800 microns away. Why is it 800 microns away? Because in the rules-based approach, sometimes that little muon just got glued to the electron coming out of there because the angles or whatever, and you naturally get some of those wrong. But in the AI approach, we don't even have that. It just gets rid of it. It doesn't even see that as an issue. It doesn't see that kink that way. It looks at it from a very different perspective. So these are the things that are happening that AI can do that allows us to have a complementary thing to the more logical way that we view ourselves. So anyway, with that, I'm going to just wrap it up here. You may have some questions. I try to make it kind of fun and intriguing as a challenge, but it's a fundamental, lots of fundamental things going on our R&D. We have a number of test beam campaigns this year. Like we hope to get to the beam 2 or 3 times this year to do various things before they shut it down for 18 months for an upgrade of the facility. And we have to make decisions on calorimeter. There might be a prototype like with Xenon if they do get funding, but they're running out of time on that one. And there's a lot of work I didn't talk to you about: electronics triggering, digitizers adapt, which is super going on like mad right now. We had a lot of trigger meetings in our last collaboration meeting of people finally getting their head around how complicated it is to, again, be looking at these events that are overlapping in space and time, and where do you put them and how do you store them and blah, blah, blah. So that's just beginning to start. And I think that's it. Questions, feel free. Sure.
Can I ask a question on the machine learning? So why don't you use convolutional neural networks?
You know, I
image-based
have to say, I'm kind of sort of ignorant compared to some of you guys about this. Omar could give you an hour speech on all these things that he may have told you. I just butchered all the wrong words here a little bit. What did you call it? A convolution?
Convolutional neural.
I don't, honestly, I don't know. I've not, he's gone so deep into the literature of what people are doing, and I haven't done it myself at all. And so he's popped up with these things.
So you do use only simulations for training data,
Yes, yes, exactly.
but then how are you sure that your simulations is related to the data itself?
Well, since we don't have any data, we have to start the process by having just as realistic simulations as we think we can get. So what we're missing, so what we do have is, it's a great question. So what we do have is, for the lysocalorimeter, which is the simulating thing, we do have those waveforms. So we could put in, we have, you know, obviously we've been to the test beam, so we have the responses of those detectors. They're in there. So they go in there with their noise and with their stuff like that we see. We don't have like pretend resolution on those. What we don't have in there yet is a good model of the ATAR. So what's happening right now, sort of almost urgently right now, is these test beam kind of measurements and stuff you saw with the Van de Graaff and so on and so forth. We need to get those, we need to get their waveforms in as hits that then represent something that we have to, you know, double back and take out like that. So right now we have a little bit too much truth on the ATAR. You know, maybe we smear it a little bit. It doesn't necessarily mean the real thing. And that's where we are right now. We do have, on the other hand, a very good model of the beam flying back, the beam and the backgrounds of the beam. Only, you know, the beam comes in, we can make the beam whatever focus we want. We can make the beam hit the target all we want, you know, practice. But then we have realistic beams where only like 80% of it hits the target and the rest of it flies by and hits cables and stuff. We have cables in there and plexes and stuff like that. Huh?
Pile up and so on.
We have all that junk in there, so we get this pile up. So the green things with pile up tend to be based on, and also the timing, you know. So it's a learning process. We just started that. Yeah, to me, the moment I started to see this, I got 100% convinced this is the only way to do the experiment. And so I've been really supportive in pushing that effort, but I'm personally not. You know, I haven't done the work that he's done, which is lots and lots of digging into the literature. There's this one paper he quotes that has 200,000 citations on it that everybody, a couple of you guys are nodding because you must know about it.
Yeah.
And so that one,
Transformers. Yeah, from
yeah,
Google.
that one.
Yeah, I don't think CNNs can use as much information as the transformers can, right? The image-based.
Is there so much information there?
Yeah.
from
If you go back,
years?
I think there is. If you go back to the slide where you showed the, maybe one more.
Back again.
One more. No, I think
So you have
forward.
positions, times, and multiply by the number of layers.
I think CNNs would still just basically be replicating what our eyes can do, whereas a transformer can, I think what Sarah was saying, use more. And I think, if I remember correctly how these work, CNNs are like feed forward only models, whereas transformers will also go backwards.
Okay.
And so you can learn a lot more information through that.
Yeah, it was kicking things to different things that we're learning, modules that we're learning something about, and then, yeah, it was an interesting
Sheet
flow
of
charts.
motion. There's a lot more than just timing, location kinds of
Yeah.
things from these detectors.
Yeah.
It's more than that in a way. That's why I was trying to say it's like learning It's learning the value of things that are relationally there. So it learns to ask its own questions. It's the way in a simple way he describes it. It learns to ask its own questions of things that matter that you might not notice or ask. I think it's kind of cool that way, yeah.
Couple of questions. One is, what's the challenge in growing lysocrystals?
What's the what?
What's the challenge in growing lysocrystals? Are there applications for these type of crystals?
Lysocrystals? They're using PET scanners everywhere. Little pieces of that, yeah, because you can see this timing.
Yeah.
And you can see the resolution. So a PET scanner is going to be 2 511s and so on like that. And so, yeah, that's a standard thing that companies might make, the little ones. They're very expensive is a problem. Otherwise, people would probably use them in more calorimeters. Everybody dances it. So they are beginning to use them in different applications. So you see these sort of lyso sort of timing detectors that they put into various things with lyso fibers and stuff like that. There's somebody wants to build a little lyso converter for a 3rd generation mu to E gamma experiment, a little thin converter that picks off the time and has good and measures the energy of the electron before it converts. So, you know, it's a neat thing to learn about crystal growth too, quite a bit. And actually, you know, trying to get the uniformity and trying to measure that along the longitude and how well you have to do it. And another really cool thing is if anybody's ever done the light Monte Carlo of a tapered crystal, it's a pretty famous problem. They're very focused and compared to a rectilinear one, and you have to abate that by some tricks. You have to scratch the sides, or you have to. All of the big calorimeters in high energy physics have gone through this process of what do you do because the light isn't uniformly collected. So that's a really tricky one that you know suddenly you go down the street of Monte Carlos and then roughening. It's called roughening even. It's a word, roughening, and there's even a whole language in the crystal grower community about roughening and how much roughening. Ours are roughened on one side.
So the tracker used to be kind of like this inner semicircle shape, but now your diagram shows it's kind of this U shape. What was
I
it?
didn't mention the tracker. You're right.
This is kind of.
I blew right by there in a fit of hurry or something. But
I'm just curious what the
I
design.
do want to tell you about that because this is an open problem and I don't know the answer to it. So I'm fishing around. This is a cartoon. This is literally a cartoon. So what matters is when you start to really analyze the tracks that I was showing you, and either done by the rules-based approach or otherwise, everything works just great, like up to about here. Just no problem. The rules works real well to here too, no problem. As soon as the tracks start going up in this direction, kind of along the planes, you're not getting enough hits. You're going in these glancing angles. You're going in dead layer gaps. It's a super problem. And so we think we need, forget this shape now in your mind. We think we need some kind of a cylindrical tracker that goes kind of around here like this. And it has to have parameters that are complementary for this experiment. And I was telling some people that most of the time you go to the tracker store and people want to advertise what extraordinary position resolution they get. We don't need that. We don't need to know the track at that angle. We need it a little bit, but we just need to know it's going somewhere. But we need to do it fast. So we need to have nanosecond timing. We don't need micron resolution. So we're running into people who have beautiful detectors that have, 15 nanoseconds or 10 nanoseconds. So that's long compared to pion lifetime, so you just don't want numbers like that when everything else is clicking along at sub-nanosecond. And or that's too thick. Now you go through a positron with a couple of MeV in it, and what's the probability it makes it through there without annihilating? And it gets to be a huge problem. I grabbed a sample from your lab, and I don't know if I crushed it, but just these little,
Don't tell Jeff. I gave him a tiny scrap of honey.
I got a scrap. Where is Jeff? He gave me a tiny scrap of your honeycomb just to remind me of how small and important a little light material could be to hold something. We have no idea how to hold the ATAR up in the air. We have no idea. We got it really easy on PowerPoint.
I was wondering about your cabling and your, support structure.
Okay, so we are working at the lab on these flex cables, and we're trying to look for, have you guys ever heard of what's called a rigid flex cable? Anyone? There are some developments of rigid flexes that we may have to go with, but the flex cable, then the impedance of the flex cable is a problem. So the impedance matching to what's called the fast 3 amplifier has to be kind of 110 or 120 ohm, and there's nothing like that. So you try to develop these flexes. Now, where can you get them? You can go to China where they can make custom ones for you, where it's a little tariffy and so on. In our country, I don't know if they have anything. And we are, you know, you're at the bench with these little samples trying to do that. And the signal has a problem. If the flex is like 10 centimeters long, that's a problem. We kind of got it so the crosstalk is minimal to okay there, but and now we're doing it at 2 centimeters. But all of this designs what you can do, and it seems like it's really far away from the cartoon when you start talking about I can't get the flex cable in this cartoon, you know, because it's coming out here at an angle like this or something. And how do I hold it? And now suddenly you have to add materials to that. And therefore the fiducial volume, which was going to be all the way back to here, maybe that's not a good idea. Maybe you know, we sometimes like, maybe we should just stop the fiducial volume around here, which would save me a lot of money. Like if I had about, this is a $9.2 million worth of LISO here, but it's, you know, this is maybe $5 million worth of LISO here. But if this stuff isn't going to be useful, I don't want to buy it. So that's the kind of thing we're doing. It's really fun. I mean, people are, and we are, I did say we have a postdoc opening to work on this 8-hour thing, and we have a research scientist opening to do this too. So it's a thing that's come up this just recently, and also one for Project 8, I think too. So it's great. This is why you come in the morning. You come in the morning because you run into people who want to talk about this and try to figure it out. So I can say it's exactly opposite of something like G-2, where you're just marching down the street and making sure you don't trip over a small snail.
I have a question about lepton universality, or your original motivation. Presumably something is known about it, for example, from W decays.
Yeah, sure.
High
All of
energy.
that, yeah, all of those are
I mean,
many times weaker. Exactly correct. So lepton universality measurements are made by lots of tau decays, in fact, or B decays, and many. In fact, there's a lot of excitement about violation of lepton universality in some of the charged B decays, where they you know, multiple standard deviations away, like 10% violations. So that kind of physics would be very different than this kind of physics. Is what happens in that upper sector. But all of even the mu to E's and so on, all of those, there are many measurements of mu to E universality, but they're just much weaker than the one I showed you there from the high energy ones. Yeah, everybody's doing that with decays that they can, pretty standard test. But the kind of violation that people thought was new physics in the B decay sector in the last bunch of years, part of it went away because they had their electron tracks completely wrong. And then they fixed it and it went right over universality. That was a big deal in LICB for a while. Unfortunately, they just analyzed it wrong. But when you look at that data carefully, there's just no chance that they could be down at levels like this. So that would be an extremely different kind of physics case that they would, you know, have created a particle which did something weird in that way. But it wouldn't be what we would see. So we used to advertise that, and then we just scrubbed it off our slides, because we thought we're not connecting to that physics.
One last question from John online, and then.
Hey, Dave. Yeah, thanks for the nice talk. I was curious about your active target.
Yeah.
In particular, the timing characteristics, and whether you could use that for that plus maybe DDX to distinguish electrons and muons, or do you do that?
Well, the timing of the target tells you which hits go to the same time group. And then the DDX tells you whether they were one type of particle or another. So in that sense, yes, that's blended in completely. But you can't tell the difference between one hit in that time group and the next one and the next one, that you do not know that.
Okay.
Those dots in this group I had here later.
Right.
Yeah, everybody brings this up, and we always have to remind them that's not what we mean by good timing.
Okay. Yeah, that was what I was curious about, whether you could, you know, distinguish hits just from the timing.
Yeah, it would be great, but there's just too much noise and too much stuff in any kind of a timing signal. If that's what you were relying on, you're probably going down a dangerous street.
Okay, thank you.
Sure.
Let's thank Dave again once more.